Hello students, welcome to lecture of Kinematics and Theory of Machine. Myself Patel, and we are going to solve some other example from our chapter Velocity in Mechanism by Relative Velocity Method. So we have solved 2 or 3 examples in the last lecture. So we will solve some other complicated mechanism. But now I am not going to find the exact velocity of every link in this mechanism, but I will show you how you can draw these perpendiculars and you will draw the velocity diagram. This is our practice examples. Okay, so let's start. So this is our example number 21 from question bank. The length of various links of mechanism, as you can see on the screen, the length of every link is given AB and DE 150 mm, BC and CD 450 mm, EF 375 mm. The crank AB makes an angle of 45 with horizontal and rotate about A. This crank, you can see this crank AB, which is fixed about here like this, like here. This crank, if I am show you like this crank is like connected to here and it is rotating with respect to A. Okay, right now this position is given here. So in a clockwise direction at a uniform speed of 120 rpm. So rpm of this crank is given, and you can see on the screen this direction is given, this clockwise direction. Okay, so check this. The lever DC, this lever DC is oscillate about this fixed point D. So here you can see this D point is also one type of hinge here, and with respect to this D point, D is oscillating with respect to this crank. It is moving here like this. Okay, like it is oscillating with respect to this DC link, and on DC link this E link is there, which is connected to this piston, and which is with respect to this DC link, it is reciprocating this F. Okay, F, which is a slider. So now we have to find here the velocity of F and angular velocity of DC. Okay, so let's start. So as you know, the space diagram is very important in a velocity analysis, because minimum 2 marks is given for this figure to draw in a answer book. Just draw this space diagram in our answer sheet and taking some scale. So as you can see the dimension here, which is a 375, which is the largest dimension in this figure. Okay, and smallest dimension is you can see this is a 150. Okay, so we have to choose some scale here. Let's see how you can choose this scale. So first of all, we have to descale. We have to descale this diagram, because we can't draw 375 mm in our sheet. Okay, so how much we have to descale this? So we can take the 1 mm in our drawing is equal to 3, 4 or 5, any suitable scale. So I will take here 10 mm in our diagram will be in actual is equal to 50 mm. So 5 centimeter in this mechanism will be 1 centimeter in our drawing. So we have taken the scale, which is a 1/5 here. Okay, which is a D scale. Okay, so 1/5 we will take here, and for drawing the velocity diagram, we need the velocity of any one link, which is given by the RPM. You can see the RPM is given 120 RPM. So using that 120 RPM, okay, using that RPM, we will find the velocity. Okay, so check this. What we have? 120 RPM, angular velocity of B with respect to A, 2 pi n upon 60. So we will get the angular velocity, and AB link is given here 150 mm, so we will get in meter, because linear velocity is angular velocity into length of that link. So angular velocity 12.56 into 0.15, you will get the linear velocity of this link B, and in this link B with respect to A. Okay, 1.89. So now we know the velocity of one link, 1.89. For that we need the scale here. We will take the 10 mm is equal to 0.25 meter per second. Okay, remember that always this scale is totally depend on us, how we can, what scale we choose. Okay, it is totally depend upon whatever the space we have and how you will draw. Okay, answer will be similar for any. So now 10 mm is equal to 0.25 meter per second. So what will be the length? What will be the length of our first vector, which is AB vector? So first of all, 10 mm. So we have to take here like this, as you see, you can see here, 0.25 meter per second is equal to 10 mm. So our velocity is 1.89. So what will be the length for that vector? For 0.25 10 mm, so 0.189, what will be the length? Check this. So our length of first vector will be 75.6. Okay, 75.6. Draw the velocity diagram. As you know the rule, all the fixed point will be on the same place. So first of all, how many fixed point you can see on the screen? So this A and this D is a fix. So I will put here like here. All the point on a space diagram, we are writing here the capital in capital, and in velocity diagram we are writing that in a small. And in acceleration diagram, which is the next chapter we will learn, in that this in acceleration diagram we will put A dash and D dash. Okay, so remember that. So now we know the A and B, A and D we have located here. Now velocity of B with respect to A. Direction, as you know, the direction will be perpendicular to link in this direction, because angular velocity, you can see this arrow here given. So in this direction I will draw the line parallel to this perpendicular using the set square, and length of this link, you will get here this point, which is the B point. Length, you know the length is a 75.6 mm. And we have finded here the vector for the velocity of B with respect to A. This is our first vector. Now, as you know that with respect to B, velocity of this C point will be perpendicular here, like perpendicular. Velocity of C with respect to B, maybe in this direction, or velocity of C point with respect to B perpendicular to link in this direction or in this direction. So we will draw perpendicular here like this, and we will draw from this B point, but we don't know the magnitude right now, so we will just draw the like perpendicular here. So we will draw with respect to velocity of C with respect to B. So C point will be on this line. Now this C point is, you can see this C point is also on this DC link. So with respect to D, with respect to this D point, velocity of C may be in this direction also. Okay, so we will take the perpendicular to this DC link, and we will draw this perpendicular from this D point. Okay, like here. Okay, so this perpendicular I have drawn from this D point, and intersecting point, as you can see, this intersecting point will be nothing but C. This intersecting point is a C, and we will join these D and C. We will mark this line after that and erase the other lines here like this and this. So you can see here this vector, if you write here, this is the velocity of C with respect to A. Okay, and this line, BC line, if you are writing here, this is the velocity of C with respect to B. So you can see that one by one, every point we have to locate that in a velocity diagram. Whatever point they give in a space diagram, we have to find these points in a velocity diagram. So we have finded this A point, B point, C point and D point. Now we will find this E and F. How you will find this E and F? So first of all, you can see this E point is on a DC link, and we have finded this DC already. Okay, you can see we have finded this DC length already in our velocity diagram. So just we have to locate this E point on this velocity diagram. How you will locate this E point? So rule number 4, velocity of any point on link, we can find this using this ratio. So you can see this E point is here. So using this ratio, how you will use this ratio? So you know that distance here from C to E and C to D. You know these two distance here. So we will take here the ratio capital CD divided by capital CE. You can see this CD is already given. CD is given 450 already. And if you measure this, you can find here CD upon CE. Okay. Is equal to same dimension CD from our velocity diagram. This CD distance, this C to this D distance, CD distance divided by this CE. Okay. We know this value, we know this value. 3 value is known. We can find this small CE and you will find this C to E distance. So you will measure this C to E distance and you will locate this E point here on this velocity diagram. So now we have located this E point. Now we will find the velocity of F slider. Okay, so you can see with respect to E, F, you know that whenever any point we consider on a link, we will find the direction by perpendicular. So first of all, for this F slider, we will take the perpendicular here with respect to E. This perpendicular we will draw here perpendicular like this because we don't know the right now the magnitude. So the slider F with respect to E perpendicular to link, we will draw this line here. But as you know the rule number 3, the slider is sliding. You know the slider direction of slider. You can see this is the horizontal line. This is the sliding in a horizontal line. So I can draw one horizontal line from our origin. You can see this horizontal line and intersecting point between these 2 points. This will give me the F slider here, this F point. And if I connect these lines here like erase the other extra lines. So you can see this is our velocity diagram. Okay. And if you want to find the velocity of this F, you have to just measure this distance. Which distance? This distance you will measure this and A to F distance will be in mm, but you have to convert that using that scale here and you will find the velocity of F. Let's start find the velocity of F here. If you measure this distance D to F, you will find 28 mm. Remember that 28 mm you will find here. Okay. But you have to use this scale here. 10 mm is equal to 0.25. So for 28 mm, what will be the value in meter per second? So you can see here for 10 mm, 0.25 meter per second. So for 28, you will find 0.75 meter per second. So this is the method. You will find the velocity. If you draw complete the velocity diagram completely, perfectly, you will find the velocity of any link or any point on a link. Okay. So next, we will find the angular velocity of DC. So for that, first we need the velocity of DC. So DC link, you can see this DC, D to C distance. This distance D to C, which is you can see 90 mm, but 10 mm is equal to 0.25. So 90 is equal to, as we have to calculate that, and you will find 2.25 meter per second. And using this value, you will find the angular velocity of this mechanism. Okay.